Good afternoon, I'm Bill Langdon. I'd like to talk to you about my EuroGP poster, Incremental Evaluation in Genetic Programming. So the idea is we're going to exploit the fact that in GP, the functions and terminal sets have no side effects, and that they are pure functions. Although they're pure functions, they can still lose information in the sense that they take two 32-bit arguments and generate a 32-bit answer. What we show is that the trees can be evaluated in any order, and in particular, we're going to evaluate them from the change point and show that the parent and the child can be phenotypically similar, even though they're genetically different. And it's this information loss that gives rise to a smooth landscape for GP. So here on the left-hand side, we have a tree which is being evaluated in the conventional top-down recursive fashion. And then on the right-hand side, the same tree being evaluated from the bottom up. So on the left-hand side, we start with the subtraction node at the top, number 1. We evaluate its first leaf, 0.026, and then we need its second argument, which is this division node. And we recursively evaluate down until we've evaluated the whole of the tree. But we can get exactly the same answer if we start from anywhere else in the tree. So in particular, if we start from the leaf minus 0.826 and work upwards, we'll come to the multiply operation. Multiply requires a second argument, of course. And what we show is that it returns 0.59368, which is exactly the same answer as it returns in the conventional top-down recursive evaluation. And in particular, we trace all the way up through the whole of the tree. We'll see that it returns exactly the same answer as it did with the top-down recursive evaluation. If we look at parent and child, if they are identical apart from the inserted and removed subtrees. So if those subtrees happen to be identical, then the parent and child will be identical, and so of course have the same fitness. If the removed subtree evaluates the same answer as the inserted subtree, so we can evaluate each subtree independently, if they happen to have the same value, then the whole of the tree will have the same value. So we have genetic difference, but we still get identical fitness. And the interesting case is where the subtrees evaluate to different values. What happens then? And we can find out by evaluating from the change point up to the root node. And what we'll see is this a progressive fall in the number of test cases where the change is visible as we move towards the root node. So remember that the trees are identical apart from the change. The fitness evaluation will be identical except on the route from the change to the root node. And what we're going to do is we're going to evaluate the parent and the child all the way along this route. The point being, if at any point on a test case, the parent and child are identical, they'll remain identical or on the rest of the route to the root node. So we have a case where we can have a semantic difference between the parent and the child and still get identical fitness. And that's what this little picture is trying to show, is the original parent are the nodes in black. So those are the common part that's common between both parent and child. And then in blue, this is the inserted one. And so we can see that the child fitness values are in blue, and they are different between the parent and the child. But if we progressively move from the division point up, then they may at some point become identical. And if they become identical, then they'll remain locked identical for the rest of the evaluation. So this is a picture showing a large tree where this happens. The red subtree is the code that's been inserted, so it's quite a large change. But as we progressively move up the blue chain of nodes towards the root node at the top, then the difference between the parent and the child gets progressively smaller until by the time we reach the top of the blue chain, the parent and child evaluate to exactly the same value, and there's no difference in their fitness. This graph is showing the same example, so we can see on the left-hand side, we start off with on all 48 test cases, there's a difference between the parent and the child. But as we move up the tree, by the time we've gone up 13 nested levels, then there are 3 test cases where the values are identical. So the parent and child evaluate to the same value on those 3 test cases, and they will remain locked together all the way from there to the root node. And we can see that the number of test cases where this is true progressively increases until by the time we've got more than 144 nested functions, then all test cases are identical, and the fitness of the child and the parent must therefore be identical. So we could see that as we have crossover points which are further from the root node, they tend to have less effect. You might want to exploit that to design your crossovers. So if you wanted to have a smooth fitness landscape, you might put the crossover points farther from the root node. Conversely, if you wanted to make large changes, you might want to put the crossover points close to the root node. What we see is that if the disruption is there's no disruption between the parent and child, then selection will quickly converge the population in the sense that everybody in the population has the same fitness, even though they are genetically different. And I'd like to stress that all of this dissipation of disruption comes about through information loss. And so we're seeing that the information loss is tending to give a smoother fitness landscape